So dear students, in today's lecture, we will discuss that how can we convert a given transfer function to a particular state space form, right? So as we have already seen that we can convert a state space to the transfer function, the state space model of given linear time invariant discrete time system to the uh, transfer function model of the same system, right? So in today's lecture, we will discuss that how we can convert if we are given a particular transfer function of a discrete time system, how we can convert that transfer function to the state space model, right? So we generally call this as canonical form. So there are various canonical forms which we can derive from the equation which is given here. Okay, fine. So if we have the difference equation, by taking the z transform of the difference equation, we can derive this transfer function. Okay. Now, if we have the transfer function here and we have to find out the state space model, so how we will do? So in that case, we have certain canonical forms which are known as controllable canonical form. Then we have observable canonical form. Then we have Jordan canonical form, right? So the first is the controllable canonical form, which is also known as first companion, right? So this is also known as first companion. So in this, what there is a particular procedure or method or way of deriving the state space model of the given transfer function. So as this equation, let us say this is some equation number one. So now uh, we can derive the state space by bifurcating the given transfer function in two parts. Let us take it as x yz upon xz, and let us say this is some okay, this is xz into z by uz, right? So now, okay, so we can bifurcate the given equation like this. So in this we have the two parts, beta naught Zm plus beta 1 Zm minus 1 plus beta 2 Zm minus 2 and so on, right? So let us say we have beta m. Okay, so if we take m is equal to n, so in this we will consider, because m is either less than n or it is equal to n, right? So we'll take that m is equal to n here. So if we take m is equal to n here, so this m will be converted into n. So let us do it, let us change it first. So this is 1 into 1 by, we have Zn raised to the power n plus alpha 1 z raised to the power n minus 1 plus alpha 2 z raised to the power n minus 2 and so on. And this is alpha n, right? So let m is equal to n. So in that case, we have, let us equate them. So this particular part of the equation will be equal to this part, and this particular part will be taken equivalent to the denominator part, that is the poles, right? So let us write it. So yz upon xz. So this is equal to beta naught z raised to the power n, because we have taken m is equal to n, plus beta 1 z raised to the power n minus 1 plus beta 2 z raised to the power n minus 2 and so on, right? Up till beta n, where betas are basically the coefficients of, real coefficients of the numerator of the given transfer function. Similarly, this is equation 1, for example, this is, let us say, equation number 2, for example, and this is, for example, equation number 3. Similarly, we have xz upon uz, right? So xz upon uz will be 1 by z raised to the power n plus alpha 1 z raised to the power n minus 1 plus alpha 2 z raised to the power n minus 2 and so on up to alpha n, right? So this is, for example, equation number 4. Now, so let us simplify the equation 2 and find out yk and similarly xk, right? So this was xz basically, okay, in equation number 3. So it is yz by xz here. So we have multiplied here with xz. Now we'll take, this is for example equation number 5. So we'll take the inverse z transform. So inverse z transform of equation 5 gives, so we will have yk here and this is beta naught. Now from the advanced shift theorem, Zn into xz will be equal to x k plus n, right? This is, so if we take the z transform of x k plus n, it will give you Zn into xz and then some initial conditions, because we are deriving the state space from the transfer function. And as per the definition of transfer function is the ratio of z transform of output to the z transform of input with initial conditions 0, right? Okay, so that is why we are not considering those initial conditions here, right? So we have this one, then we have beta 1 and z in raised to the power n minus 1 into xz. Now let us understand this one. So if you see this part here, so this part can be written as z raised to the power n into z inverse into xz. So that means z inverse into z raised to the power n into xz. So that means now the transfer, the inverse z transform of this one is equal to x k plus n. But since this part is delayed by one sample, z raised to the power minus 1, so we'll write here x k plus n minus 1, right? So the inverse z transform of this part is x k plus n minus 1. So in the similar manner, we have the next term beta 2. So here we have Zn. So let us write it here, z raised to the power n minus 2 x z, right? So it is z raised to the z inverse square into z raised to the power n into xz, right? Now that means this particular term has been delayed by 2 samples here, right? 2 samples. Okay, so this would be x k plus n minus 2, right? And up till, so here beta n into xz, so we don't have, we have z raised to the power 0 here, z raised to the power 0 here. So that means we have beta n x k, right? Beta n xk. So this is, for example, equation number 6, right? This is equation number, let us say 6. Now, okay, so similarly, take inverse z transform of equation, which equation? Equation number 4, right? So this is equation number 4 here, this one. So let us take this. So x z is equal to, sorry, x not x z is equal to, so it is x z into z raised to the power n plus alpha 1 z raised to the power n minus 1 plus alpha 2 z raised to the power n minus 2 plus alpha n and is equal to uz, right? So this is equal to uz. Now xz into zn, xz into this, xz into this, xz into this. So if we take the inverse z transform of this one, so zn into xz will give us xk plus n, right? Then we have alpha 1 and xz into z raised to the power n minus 1. Okay, so that means zn into xz has been delayed by one sample, so it will give us x k plus n minus 1 plus alpha 2. So this would give me alpha 2 into x k plus n minus 2 and plus. So this will give me x alpha n x k is equal to the inverse z transform of uz will be uk, right? So this is, for example, equation number 7, right? Now, since because the order of the system is n, right? The order of the system is n, right? How? Because you can see the power of denominator is n and we are considering it for m is equal to n. So the order of system is n. That means there are n state variables. There are n state variables. That is x1k, x2k up till xnk, right? So our purpose is our purpose is to convert the given transfer function into the following form, right? And that form is x k plus 1 is equal to fxk plus guk and yk is equal to cxk plus duk, right? Where xk plus 1 is a column vector which contains all the dynamics x1k plus 1, x2k plus 1 up till xnk plus 1, right? And xk is also a state vector. It is a state vector which contains all the state variables x1k, x2k and up till xnk, right? So this is, for example, equation number, some equation, let us mark it as some equation number 7. This is, for example, 7. Now because we have taken we have converted the given transfer function in terms of xz. Okay, so yz has been obtained in terms of xz and uz is also in terms of xz here. So now let us, if we assume, if we mark that let x1k is xk, that is, this xk is nothing but, let us say it is x1k, the first state variable, right? Now if we replace k with k plus 1, so x1k plus 1, this is equal to xk plus 1, right? So this means we have taken the next state variable, right? So next state variable, that means this will give us some next state variable which is, let us say, xk x2k, right? This will give us some x2k, right? Now Now if we put k is equal to k plus 1 here again, so x, uh, so let us take it as x 2k plus 1, right? So this is equal to x1 k plus 1 plus 1, that is x1 k plus 2. Now let us not take this one every time, because we have already assumed that it is equal to this one, right? So x1 k plus 2. Okay, so now we have advanced the state, and now we have got the new state variable, that is, let us say, x3 k, right? Similarly, if we put x3 k plus 1 is equal to, if we replace k with k plus 1 in x3k, so this will give us x3k plus 1 is equal to x2 k plus 2 is equal to x1 k plus 3, right? So this will give me a new state variable, which is, let us say, x4 k, right? Now if we see the sequence, so here we have 4, here we have 1, here we have 3, right? So if I keep on doing it like this, so I'll get x and k, right? If I get x and k, it must be equal to, it must be equal to n. So x1, because every time I can see that xk is equal to x1k, x2k is equal to x1k plus 1, x3k is equal to x1k plus 2, x4k is equal to x1k plus 3. Okay, so if you want to write it, you can write it like this also, x k plus 2. You can write it like this, x k plus 3. Now why I am doing this, I'll tell you. Because if I see the inverse z transform of the equations, I'll see that here I have x k plus n, x k plus n minus 1, x k plus n minus 2, and so on. Here also I have this in terms of x k plus 1. I don't have this in terms of x1k, x2k, x3k, x4k, like x and k. So I have to convert the equation number 6 and 7 in terms of x1k, x2k, x3k, x4k. That means in terms of state variables, right? So that is why I'm doing so. So if x and k is, it can be equal to x1 k plus n minus 1, right? So if you put n is equal to 1, let us put n is equal to 1 here. Okay, so x1k is equal to x1k plus 1 minus 1, so that is x1k. Okay, so I'll put it equal to x k plus n minus 1 here, so it is equal to xk. So I started with this assumption only, right? I started by taking x1k is equal to xk. So if I put n is equal to 2 here, let us put n is equal to 2. So x2k is equal to x1k plus 2 minus 1, that is x1k plus 1 is equal to xk plus 1. So this term is also true, second term. Similarly, third term will also be true. So in this way, by doing so, I will reach to a conclusion here. So I'll convert the uh, terms of x in equation number 6, 5 and 6 in terms of x1k, x2k, x3k, and xnk. Now let us advance this one. Okay, so this is some equation. Now let us advance. So if I want to take xn, if I want to take xn k plus 1, if I want to take the dynamics, right? So x and k plus 1 shall be equal to what? It shall be equal to x1 k plus 1, right? So we'll reduce by 1. If you see here, 2, 1, 3, here 1, here 2, 4, 3, 5, 4, 6, 5, n minus 1. Okay, k plus 1, x1 k plus n. If you keep on doing so, you'll get x and k plus 1 is equal to x1 k plus n. Now, and that is equal to, hence, x k plus n, because you have taken xk is equal to x1k, right? So if you see here, xk plus 1, xk plus 1, So xk plus 1 will be replaced by xnk plus 1 in equation number 5 and 6. Hence, from this analysis, we summarize as some. We'll summarize this and we'll summarize it like this. So, the summary of this analysis here, this analysis is given here. So from in this one we can say that, so here if you see x2, then here x1, 3, then 2, 4, then 3, and then n minus 1, right? So x1 k plus 1 is equal to x2k, 2k plus 1 is equal to x3k, and in this way we have this one. So if we take equation number 7, so in equation 7 we have all these elements here, so we'll write it like this. Okay, so let us write the equation. So if you see in this equation, let us replace xk plus n. So xk plus n is x1k plus n, which is xnk plus 1, right? So we'll write it as xnk plus 1. Similarly, we'll write for xk plus n minus 1. So xk plus n minus 1, this term. So this term is equal to xnk. So alpha 1 xnk, right? Then you have alpha 2. Okay, so then we have xk plus n minus 2. So we can see here 2, 3, 4, and say previous to this it must be xn minus 1 here, right? So alpha 2 xn minus 1 into k, right? And in this way we'll keep on writing it until, so alpha n minus 1 x2k plus alpha n, last one, into, so here we have xk, sorry, so x1, because xk is equal to x1k, so we'll write x1k, and this is equal to uk. So as you can see here, let us say this is equation number 9, right? So this is equation number 9 here. So as you can see in this, we have now this equation in terms of x and k, x nk plus 1, x and k, x and minus 1, and so on, x2, x1, all these, now all the state variables have been included here, right? So if we rearrange this equation in terms of x and k plus 1, so let us rearrange this in terms of x and k plus 1. So x and k plus 1 will be equal to, so we can take all these elements on the other side of the equation and we can simplify this equation, right? So let us simplify this. So on simplifying equation 9, so in terms of x and k plus 1, we have taken all the elements on the other side. So let us say this is equation number 10. So that means here x1k plus 1, x2k plus 1. So if you see the hierarchy here, if you see the sequence here, so we are reaching to this thing. We are reaching to this thing here, right? x1k plus 1, x2k plus 1. We are finding all the dynamical equations, state equations of the given system. So we'll write x and k plus 1 is nothing but equation number 10. So I'll write equation number 10 here, right? So this is, sorry. So this is equation number 10 here, this one. So this is equation number 10. So you can refer equation 10 for this, right? So now we have got equation 10 here. Now let us take equation number 6. So let us take equation number 6. Now let us convert equation 6 in terms of x n k, x n minus 1k, x2k, x1k, right? Let us convert that equation in terms of all the state variables. So what is equation number 6? Equation number 6 is yk is, sorry, not is equal to, sorry, yk, sorry, yes, is equal to beta naught xk plus n plus beta 1 x k plus n minus 1 plus beta 2 x k plus n minus 2 and so on up till we have uh, so beta n xk, right? So this is equation number 6, right? So now let us see xk plus n. So let us take xk plus n. Xk plus n is x and k plus 1. So let us replace all these things here, right? So by replacing, we get equation number 6 modified to the following equation, right? So let us modify this one. So you can see here we have replaced all these in terms of x1, all state variables, right? So for example, this is equation number 11. Now the output equation of a state model yk is generally given by cxk plus duk, right? So this is the standard form. So you can see the output equation, it does not contain dynamics, right? It does not contain dynamics. But here in this equation, right, in this particular equation, if you see in this equation you have a dynamic term, right? So but this is a dynamic term, right? So what we'll do, we'll replace this term. Okay, so now what we can do is we can replace this particular terms by equation number 10. Okay, so we can substitute equation 10 in this, right? So what is equation 10? You can see here what is equation 10. Equation 10 is x and k plus 1. Okay, so we'll replace x and k plus 1 with the given equation. So if we substitute, we'll get the following result. So by substituting x and k plus 1 in equation 11 from equation 10, we get this particular form, right? Okay, now we can simplify this form further by multiplying beta naught with every element and then simplify this one. Okay, so we have multiplied beta naught with every element here and we have simplified this equation. Now there is a mistake here, and the mistake is uh, this is this term is actually xn k. So this is actually xn k here, right? And this is xn minus 1 k. Okay, so this was a mistake here, so I'll rectify this one. So here also beta 1 into xn k, and this is xn minus 1, right? And similarly so on. So these were the two mistakes actually. So now if we see here in this equation, we can combine the common terms here. So common terms are like here we have this term x and k, then we have this term here, like then for xn minus 1 we have this term, and then we have this term here, right? Similarly for this one x2 we have this term here, and for x1 we have this term. So we'll combine these terms and we'll simplify this equation further, right? So on simplifying the above equation, we have got by combining all the common terms, you can see here x n k x n k. So we have beta 1 minus alpha 1 beta naught x n k. Similarly for the x n minus 1 k term, so here beta 2 minus alpha 2 minus beta naught, and we have then all these terms here, right? So now we have some equations here. If you see, we have equation number 8, we have equation number 10, we have equation number 13. So let us take all this equation. Now let us take equation 8, 10 and 13. Now if you see equation 8, 10 and 13, so just see equation 8, 10 and 13. So equation 8 we have x1k plus 1, x2k plus 1 and this, right? So let us write all these equations once again, right? So let us write all these equations here. So we have written all these equations here collectively at one place, right? Now let us convert the above equation in standard state space representation, right? The standard state space representation is, then now let us write it. So x1k plus 1, because if you see here in this, so what is xk plus, standard form is this one. So what is xk plus 1? Xk plus 1 is this. This is a column vector, right? And then xk is also a column vector here, state vector, right? So we'll write it in terms of this one, x2k plus 1, xn minus 1k plus 1, and then xnk plus 1, right? So all the dynamics are here, right? Now this is equal to some matrix F, which is n by n matrix, so n rows and n columns. So here we have all the state vectors xk. So you can see here in this equation, here, this one, x1k, x2k and up to xnk, right? So xk, x1k, x2k up till, let us say, xnk, right? Plus then we have matrix G, which is n rows and one column matrix, right? And we have uk here. Similarly we have the output yk, which is equal to some matrix C, which is one row and n column matrix, and we have all these elements here, x1k, x2k and up till xnk, right? So now let us find out the elements of the matrices. So in this one, x1k plus 1 is equal to x2k. So that means rest of the elements are, rest of the state variables are 0. That is x1k, it is 0. That is means it has 0 coefficient, okay, and so on, right? So that means it will have x1k into 0 is 0, then x2k into 1 here, then all these elements are 0, right? Now x2k plus 1 is equal to x3k. So x1k coefficient will be 0, x2 coefficient will be 0, then after this we'll have x3k. So x3k will be 1 and the rest of the coefficients will be 0, right? And similarly we have xn minus 1k plus 1. So in this one we have 0, 0, 0 and somewhere we'll have 1 and then 0, right? Because xn will be 0 here. Now xnk plus 1. So xnk plus 1 you can see here. Sorry. This has to be corrected. So xn minus 1k plus 1 is equal to xnk, right? So xn minus 1k plus 1 is equal to xnk. So last element will be 1, right? So this is 1. Now xnk plus 1 is equal to, so it has minus alpha 1 into xnk. So that means what is the coefficient of x1k plus 1? x1k, the coefficient of x1k is minus alpha n. So we'll start from minus alpha n. Then for x2k it is minus alpha n minus 1, minus alpha n minus 1. then for this would be x alpha n minus 3, and ultimately for x and k we have minus alpha 1, right? So this is the matrix F. Now similarly, what is the elements of matrix G? This is the G matrix, right? So we can see x1 k plus 1, it doesn't have any control variable, so it is 0. x2 k plus 1, it doesn't have any control variable, so it is also 0. So then x n minus 1 k plus 1, it doesn't have any control variable, so it is also 0. But x n k plus 1, it has a control variable 1, so it will be 1 here, right? Now let us come to yk plus 1. So yk plus 1 have yk, not yk plus 1, sorry, yk has these. This is the equation. So the coefficient of x1k is beta n minus alpha n beta naught. So x1 into beta n minus alpha n beta naught, and for x2 it will be this one, and so on. We'll be writing all the elements, and ultimately for xn we have beta 1 minus alpha 1 beta naught, right? So this is matrix C, and then we have this as a, so this is beta naught and uk, right? So if you see this equation, so this equation can be written as, this is for example, some equation number 14. So let us take it as equation number 14. So this is equation 14. So we can write equation 14 as, so we can write it xk plus 1 is equal to this matrix into xk plus, then we have one matrix into uk, and then we have yk is equal to a matrix into xk plus, then we have a matrix into uk, right? So we have 0 1, and we have all the elements 0 here, then 0 0 1, and then we have all the elements 0 here, right? And then we have 0 0 0 up till this is 1, and then we have minus alpha, what is that? Minus alpha n. So then we have minus alpha n minus 1, then minus alpha n minus 2, up till we have minus alpha 1, right? So this is matrix F, right? Then we have 0 0 0, and then we have 1 here, right? Then here we have all the coefficients starting from beta n minus alpha n beta naught, and then we have all other coefficients like beta 1 minus alpha 1 beta naught, and here we have beta naught. So from this analysis we can say that this is matrix F, this is matrix G, this is matrix C, and this is matrix D. So this is the given state space model. So this is, for example, equation number 15. So the equation 15 gives the required state space model of the transfer function given by equation 1. Okay, so this is how we can convert. So this was all about today's lecture, guys. I hope you have understood it clearly. So we will discuss how to draw the block diagram of the first companion form. So the equation 15 gives the required state through controllable canonical form, right? So thank you so much.